All right, thank you very much. All right, a decade has now passed since the discovery of weakened magnetic braking in old sun-like stars. And I'm really happy to be here and report to you that we have finally traced it back to its root cause, which, spoiler alert, is the evolution of the stellar dynamo, the global dynamo. Interestingly, the sun is clearly already in this transition, and the solar dynamo is operating at something like 10% the efficiency that it was just 1 or 2 billion years ago. Okay? And might just be a coincidence, but around the time that the sun began this transition, life on the Earth emerged from the oceans onto land, and so this transition might actually influence planetary habitability in an interesting way as well. So I'm just going to review the discovery of weakened magnetic braking in rotation, describe some new observations that we've made over the last several years of the large-scale magnetic fields of some of these old stars, and then discuss the implications for the efficiency of the global dynamo. All right, so in 2016, Jennifer Van Saters led a Nature paper with the discovery of weakened magnetic braking, and the basic observation was that stars older than the sun were rotating more quickly than you'd expect if they were spinning down their whole lives like the Schumannic law would lead you to expect. The ages were from astroseismology, and the astroseismology sample from Kepler was only a couple dozen stars that were included in that initial analysis, but Kepler also measured rotation periods for tens of thousands of stars, and the temperature dependence of the spin down of the distribution of rotation periods as a function of effective temperature, so we don't have ages for all of these stars, but basically showed the expected pileup that would be predicted from weakened magnetic braking during the second half of main sequence lifetimes. Basically, stars spin down according to the Schumannic law during the first half of their lives, but then weakened magnetic braking turns off, further spin down, and they all pile up along this constant Rossby number edge. Okay? So it kind of confirmed, this temperature dependence confirmed that the Rossby number was the key parameter that controls this behavior. Now, the most recent analysis pulled not only the ages, but also the rotation rates from astroseismology from the Kepler sample, and Nick Saunders led this analysis. It's a hierarchical Bayesian analysis of the full astroseismic results, and you see this characteristic temperature dependence where cooler stars spin down for longer and to slower rotation rates before they deviate from the Schumannic spin down. And that shows that sort of characteristic Rossby number dependence where, stars with deeper convection zones have longer turnover times, and so the Rossby number, the rotation periods will be longer when they hit that critical Rossby number where spin down effectively ceases, okay? So that's the rotational basis of the discovery of weakened magnetic braking, sort of an indirect consequence of what is ultimately responsible, and that's what I'll turn to now. But let me just first give you an argument, qualitatively, for why we should have always expected this to happen in slowly rotating stars, and using the sun and how its dynamo works as an example. So if there's a single phrase that describes why slow rotation should weaken the large-scale magnetic field in sun-like stars, it's the Coriolis force. The Coriolis force is responsible for the tilt of bipolar magnetic regions as they emerge at the solar surface. And it also plays a role in the establishment of these large-scale organizing flows that we've just heard about, differential rotation and meridional circulation. So you can imagine that as a bipolar magnetic region is emerging at the surface, if it in the limit where the Coriolis force is weaker, you get a smaller tilt. That means that the weaker differential rotation has a harder time separating the leading and trailing polarities before they cancel each other out. So you get more flux cancellation. And then whatever flux is left, the weaker meridional circulation has a harder time transporting that residual flux to the poles that seeds the large-scale field for the next cycle, right? So that's the critical role of the Coriolis force. So why we should have expected the rotational dependence that we're seeing. But it also influences the other side of the dynamo loop, right? Which is the omega effect, which is what turns the existing large-scale magnetic field. Differential rotation will wind that field up, producing toroidal field at the base of the convection zone that rises buoyantly and emerges as new flux, bipolar magnetic regions. Now, if, as I just described, the large-scale field is weaker and the differential rotation is also less efficient, this whole process is going to produce less new magnetic flux to seed the large-scale field for the next cycle. And so it's a downward spiral. You have a weaker field producing less flux emergence, less flux producing that large-scale field, and it just decays together. Okay. So why do we care about the large-scale field? The simple answer is that the large-scale field completely dominates the angular momentum loss that is responsible for spin down, right? Charged particles in the stellar wind are tied to these magnetic field lines out to the characteristic Alfvén radius, and that Alfvén radius is much, much larger for the dipole field than it is for the higher order components. So you get a bigger lever arm to lose more angular momentum once you break free of the magnetic field out at that radius, right? So basically, if you just eliminate the dipole field or reduce it drastically more than expected, you can turn off spin down, okay? So in 2019, we went to the Large Binocular Telescope, effectively the largest optical telescope in the world, to observe stars that you can see with your naked eye. And we did that because we need the parts per million precision to measure the variations in the Stokes V polarization across the spectral line profile. Now, over the last 5 years, we've published a series of papers. We started with the late F-type stars, where they're rotating more quickly when they undergo this transition, so the measurements are easier, and we've gradually worked our way to the cooler and more slowly rotating stars where the measurements are more difficult. So last year, all the way down to the early K-type stars. Now, I don't have time to discuss all these results in detail, but let me just give you one illustrative example of how we turn these measurements of the large-scale magnetic field in these stars that are around this transition and combine them with other observations to estimate the wind-breaking torque. So this is a star that you may have heard of. It's called 51 Peg. And to estimate the wind-breaking torque, we're using the formalism of Adam Finley and Sean Matt from 2018. So you need an estimate of the large-scale magnetic field. That's what comes from the Large Binocular Telescope. In this case, we have a Zeeman Doppler imaging map, so you're taking these measurements of the polarization as the star rotates, different snapshots, and then you invert the full three-dimensional structure of the magnetic field that reproduces those measurements. It's the radial field that matters for the angular momentum loss, so you should concentrate on that. But in addition, you need an estimate of the mass loss rate. We're using this empirical relation from Brian Wood and collaborators in 2018. You know, there's a handful of stars, nearby stars, where you can actually directly infer the mass loss rates from Lyman alpha measurements, asymmetries in the Lyman alpha profiles. And those happen to be correlated with the X-ray surface fluxes of those stars. And so for any star that you can measure an X-ray surface flux, you can infer a mass loss rate from this empirical relation. It's good to sort of plus or minus a factor of 2. In addition to that, you need the rotation period, which you get from time series chromospheric activity measurements. And you need a radius and a mass which you can just get from the spectral energy distribution and spectroscopic parameters. In this case, we actually had astroseismology from tests to get the mass and the radius. Okay, you put all those things together and get our sample on a common scale, and you see it's not a subtle effect at all, okay? On the left side of the diagram, at low Rossby number, we're looking at relative windbreaking torque versus the Rossby number, both normalized to the solar values. At low Rossby number, things sort of agree with the standard Schumannish spin-down models. But as you approach the solar value of the Rossby number, things kind of fall apart, and you get up to 2 orders of magnitude deviation in the observations from the predictions. And that is a direct observational constraint on this weakened magnetic braking regime, okay? Now, a better way to look at this is to look at the ratio of the observed value of the torque versus the model prediction of the torque, the standard model prediction. So you can see the signature of the deviation that represents what's missing from our model. So this is a key plot here. Basically, you normalize in such a way that 1 represents agreement with standard models. Again, at low Rossby numbers, everything agrees. But as you approach the solar Rossby number, you get this strong deviation up to 2 orders of magnitude. And you see the sun is there already an order of magnitude below the standard model prediction. Now, once you get the whole sample together, this gradual onset of weakened magnetic braking becomes apparent, and the shape of that gradual onset, it was predicted in 2017, shortly after the discovery of weakened magnetic braking by Robert Cameron and Manfred Schussler, under the assumption that the sun is just mildly supercritical, the solar dynamo, and it's undergoing a Hopf bifurcation. You can ask me about that later if you want to know the details, but basically it predicts this functional form for that fall off, and when we fit that functional form, indeed we find that the critical Rossby number is slightly above the solar value, so the sun is mildly supercritical. And in our sample, that dividing line separates stars with cycles at lower Rossby numbers from stars with flat activity at higher Rossby numbers. So qualitatively, it supports this picture as well. Now, you can see this effect directly in the observations, both of the magnetic field strength, the large-scale magnetic field strength, and in other proxies. So if you do the same kind of plot for the magnetic field strength, the dipole field, you see agreement again at low Rossby and the deviation at higher Rossby. If you instead, in the background in gray there, use the chromospheric activity level instead of the dipole field, you see that the standard model prediction of the magnetic field strength agrees across the board. So it is really a deviation of just the large-scale magnetic field that the models are not reproducing. You can also see it directly in the X-ray luminosities. We're going to hear about this more later in the week from Katja. Yeah. But basically, again, same picture, agreement here. It falls apart near the solar Rossby number. These green circled stars have direct measurements of their mass loss rates that agree with the predictions that we make from that empirical scaling law. So we think this is a genuine decrease in the mass loss rate. And it all kind of makes sense, right? Because if the dynamo is becoming less efficient, you have less outward propagating magnetic energy or pointing flux. That decreases the coronal heating, which decreases the X-ray luminosity, and it decreases the wind acceleration, which decreases the mass loss rate. So it all holds together. Finally, if you're not convinced that this is an effect of dynamo evolution, just revisit some of our predictions that originally led us to suspect the dynamo in the evolution of stellar cycles from 2017. Basically, this series of solar analogs with known astroseismic ages suggested that the cycle periods were getting longer and weaker, and that would explain why the sun was an outlier in the original plot from Erika Bonvitens in 2007, because the cycle is getting longer and weaker on stellar evolutionary timescales. And this is confirmed by recent data from the California Legacy Survey of stellar cycles, where you can see that the sun, if you replace the rotation axis with a stellar activity axis, you can see that the sun is not an outlier. It's just doing what all the other stars are doing. And what they're doing is their cycles are getting longer and weaker. And that leads to the domain where we find the flat activity stars. So with that, I will just leave up my summary conclusions and take your questions.
Thank you, Travis, but you have been a bit long, so only one question, and it must be quick, and your answer super quick. Please.
Okay, thank you, Travis. This is Katja Poppenheger from ARP Potsdam. Thank you for this really interesting work. Now, I think one critical point is really the mass loss rates, right? Because as you know, X-ray flux or luminosity measurements don't really directly measure anything about the mass loss rate. It's an empirical connection there. It's nice that these 3 green circle data points seem to support this, but in principle, as you go to a regime where the dynamo might be doing something weird, maybe the empirical relation actually breaks down between Lx and mass loss rate. So what do you think about that?
Well, you can only do these direct measurements from the Lyman alpha measurements within the local bubble, basically. And so it limits the number of stars where these measurements are possible. Everything that we know, so this, you can see that the mass loss rates, so this spans basically the full range where that empirical relation is calibrated, our sample does. And so there's no reason to believe there's no reason not to believe the empirical relation. So.
Thank you.
Thank you.
Thank you very much. So please plug in.